Now let's look at a very important idea, because we have made it very clear in the beginning of the discussion that every Laplace transform that you talk about must be the Laplace transform of the response in the time domain of a system. That means it must be derived from the differential equation of the system, right? Now that idea will make it very clear in case of Laplace transform of sine and cosine. And here I request you to go back to your basic physics, engineering physics, where you have dealt with both free and forced vibration. We are selecting one simple situation where a mass is attached to a ceiling with a linear spring of stiffness k, and it is made to oscillate. And you can see that we are using x to designate its motion up and down, and this is the mean position, which is the equilibrium position, where the displacement from the mean position is 0 because it is in equilibrium position. And as it moves to the maximum amplitude, you can see the velocity goes to 0, because here at the mean position, since the kinetic energy is maximum, your velocity is maximum. Now the question is, why am I emphasizing on the initial conditions? That is very important if you are trying to convert a differential equation into the Laplace transform form, or you are trying to reduce a differential equation to algebraic equation in terms of S, right? So that is the idea. Now if I write the differential equation for this particular system, what it is going to be? It is going to be the inertia of the mass d square x by dt square, and then multiplied by mass. This will give you the inertial force, and that must be equal to the negative of the restoring force minus kx. Remember that k is a linear spring, and therefore if I looked at the differential equation of this in the most simplified form, it's going to be dt square plus k by m x, that's equal to 0. You can designate k by m by any parameter, but we did mention that this is nothing but natural frequency of the system in the initial discussions, or this is something that you have learned throughout your +1, +2 and engineering. So therefore this is something must be obvious to you. You can designate it by any letter. I would like to designate it by letter A. It would be more appropriate, because we are talking about the Laplace transform of sine at cos at. Remember that. So therefore how this equation gets translated: plus, instead of omega n square, I am putting a square, and then x, this is equal to 0. So this is the differential equation whose time domain response could be either cos at or sine at. This is the differential equation of the system whose time domain response could be either sine or cos. And how do you determine whether it is sine or cos? It entirely depends on the boundary conditions. It's going to be sine if things incept from the mean position. It's going to be cos if things incept from the extreme position. That's very important. And one of the advantages of this discussion is that you will also get a very detailed idea as to how to deal with the differential equations using Laplace transform, because that is one of the components of your curricula. So therefore this is going to be very useful. Not only you are appreciating physically what is going on, but also you are learning how to deal with a differential equation. Now let's try and convert this into Laplace transform, the algebraic equation. So how do you do that? That is using the boundary conditions. So now the equation on hand is d square x by dt square, plus you have a square, and then x, that's equal to 0. Now if I seek the Laplace transform of second derivative, remember it is given by s square x of s, because I am talking about the displacement to be designated by x, so I am getting x of s, minus s into x of 0, that is your initial boundary condition, minus x dash of 0. right? So this is what exactly you're going to get when you seek Laplace transform from d square x by dt square. You can either look up for the formula, or you can visit our discussion on differential equations for a detailed derivation of this. So this is what we are going to use here. And then if I seek the Laplace transform, constant is going to remain outside, and this becomes x of s. And that is equal to 0, because if you are trying to evaluate the Laplace transform of 0, it's going to be 0, because 0 into anything is 0. If you integrate 0, it is going to be 0. So it's a matter of common sense. So the RHS continues to remain 0. Clear? When I took Laplace transform for the second derivative, it is s square x of s. X is the term that we used for designating displacement, minus s into x of 0 minus x dash of 0, a square x of s. Now what exactly you mean by x of 0? That is nothing but the displacement when you incept at whatever point you incept. That is, you are incepting at the mean position, the first situation. The second situation is you are incepting from the extreme position. So what would be this, how exactly this equation gets simplified if I am incepting from this mean position? What would be the value of the velocity? Velocity is going to be maximum, but what about the displacement? Displacement is going to be 0, right? Very, very clear. This represents velocity, this represents displacement. So displacement goes to 0, but the velocity remains maximum. If I say the velocity is of value 1, just for the discussion, I'm saying the velocity values a are 1, whatever you can put. But in our case, what should we put? Here you have got the sine at, that is omega n, natural frequency is replaced by a, and here also the natural frequency is replaced by a. So therefore it would be more appropriate to put x dash is equal to a. So if I simplify this, what exactly I would get? S square x of s, okay, and plus a square x of s, and this goes to 0. Obviously you are starting from the mean position. This goes to the RHS, and let us say that is a. And therefore what happens if I simplify? I'll get the expression for the x of s, which is going to be a divided by s square plus a square, right? This is exactly the expression that we got for the sine at, the Laplace transform from sine at. So therefore when you reduce the differential equation for a spring mass system, it can be even for an LC system. That is, if you are an electrical engineer, instead of this you can consider an LC circuit, because L indicates the inductance, which is equivalent to mass, and 1 by C indicates the stiffness, the equivalent term in electrical engineering. And you can clearly see since we incepted with from the mean position, the solution of this particular differential equation is y is equal to sine a t. And of course, if you assume the amplitude to be 1 unity, then this is the solution. If you are incepting any simple harmonic motion from the mean position, that simple harmonic motion is represented by y sine at, which is nothing but the time domain response of the system. So it is a natural vibration, so there is no forcing function that is made 0, because it is natural vibration, and therefore this is the Laplace transform, which is nothing but the Laplace transform of the time domain response of this particular system. It is just perturbed and left, and it starts oscillating on its own. So therefore this is exactly the interpretation. So next time whenever you confront the Laplace transform, you must appreciate the fact that it belongs to a system. That is, the differential equation is reduced to an algebraic equation. Okay, now let's look at what happens if I consider this and apply it to a situation where your motion incepts from an extreme position, not from an equilibrium position. In an extreme position, what happens? Your amplitude is maximum, but your velocity is 0. And what I have assumed the amplitude to be 1, right? So now let's see what happens. So if I write the Laplace transform of the differential equation now that you are familiar with, minus s into x of 0, that is the initial amplitude, and then minus x dash of 0 and plus a square into x of s, and that is equal to 0. As usual, when you take Laplace transform of 0, it is 0. Now look at the boundary condition. That is where I have been emphasizing that boundary conditions are very, very critical for Laplace transform whenever you are dealing with differential equations. Here, the mass is starting from the extreme. That means there is absolutely maximum displacement, no velocity, because if it were to have velocity, it would have stretched further, because it is stopping and returning because the velocity or the energy is fully exhausted. Common sense, right? So therefore this obviously goes to 0, and amplitude we have assumed to be 1, and that is where the velocity also we assume to be omega n itself, because omega n into amplitude will give you velocity, and since omega n is a and amplitude is 1, we assumed the maximum velocity to be a itself, right? So that is what we assumed previously. So here the amplitude is 1, so therefore I am going to replace x of 0 by 1. So therefore what I would get x square, and plus here you have a square. Both have what common? X of s. I am collecting this term, right? And what about this term? Minus s into 1, and that is equal to 0. If I simplify and get an expression for x of s, you get exactly what you got for cos, right? So this is what exactly you got for cos. And from a control engineering perspective, this is a very, very difficult function to interpret, because you have an s term in the numerator. You will study if you are an electronics engineer, but we don't get into those details. But if you looked at this, because here the motion incepted from the mean position, you don't have an s term in the numerator. That is one of the advantages. That is, you are incepting your motion from the mean position, from the equilibrium position, right? So that is very, very important to observe. So it has been very, very emphatically said that whenever you confront the Laplace transform of a function, that means you have converted the time domain response to frequency domain. That means this is the result of the conversion of a differential equation, and the boundary conditions are very, very important. You saw that because we assumed the right boundary conditions, we could get s in the numerator, otherwise we would not have. And also here in the previous one, we assumed the correct boundary condition so that we could get only a. And what is very, very important here is that the natural frequency is a and amplitude is 1. So velocity is a into omega n, which is nothing but omega n, which is nothing but a, because 1 into a. So therefore that is what we have got. So now whenever you confront an expression for Laplace transform, you exactly will be able to relate that to particular physics. Of course, in some cases the physics could be complex, in some cases it could be very straightforward. So let me recollect what we did. We in fact started with this differential equation, which is called the 1D modeling. And whenever you are modeling a system by a differential equation, what are very, very important are boundary conditions. Now physically you are appreciating what is going on, what exactly I mean by initial boundary conditions. Here, if you are incepting from equilibrium, your displacement is 0, your velocity is maximum. That is where you start going to the extreme. There you exhaust all your kinetic energy, your velocity becomes 0, but you have achieved the maximum displacement or amplitude, and then you start coming back. And then here again the velocity will be in the opposite direction, you go up and come back, and that is how it oscillates. And when I wrote the Laplace transform expression for derivative and incorporated the right boundary condition for the first case, the right boundary condition said that your velocity is maximum but displacement is 0. So we could simplify, get an expression for sine, because y is equal to sine at is the solution of this differential equation for the motion incepting from the mean position. Now secondly, what we did, we in fact said that velocity is 0 because you have exhausted everything when you started, when you reach the extreme position. So here the displacement is maximum. So I incorporated that displacement. And then when I simplified, I could get exactly s by s square plus a square. Here, the solution of the differential equation, if you are starting from this extreme position, is y is equal to cos at. Again, amplitude is 1. Why? Because your initial displacement itself when t is equal to 0 is 1. Of course, here we have used the symbolism x, so don't get confused when I write x, because x is used for displacement. So at t is equal to 0, it is 1. So therefore, the solution of the differential equation I'm talking about is this. When you're starting from extreme position, is x equal to cos at. Otherwise, it is x equal to sin at. So this gives you a detailed appreciation of the Laplace transform versus physical systems, right? So let's move on. And also, one advantage is you have actually learned how to deal with differential equations, which I haven't covered yet. So therefore, double advantage for you. Let's move on and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.